Let you know how to derive the wave equation from the differential form of the Maxwell equations in free space. And using the Maxwell equation in free space, we can derive the wave equation, which is actually a PDE, partial derivative equation, partial differential equation, governing how the E field and B field should be generated and interact with each other. In solving the wave equation, we can know the solution to this is actually the EM wave, and we have learned the solution in the slides of chapter 33, but here just let you know how does it come from. So for Maxwell equation in free space, so actually the original form for the Maxwell equation is like this, without this red line. So actually for the electric version of the Gauss law is divergence of E field is the charge density over the epsilon naught, and here we have mu naught times the current density plus this displacement current term. So now we call it free space， 中文叫做自由空间。Free space. This is called free space, which means that there are no charge, no current density, no charge, no current density, which means the space is actually free, because if we have charges or current, then it will generate some E field or generate some B field, and as long as this E field and B field may be varying, then this varying B field and E field will also further generate the E field and B field. So it will make things more complicated, much more complicated. So as long as we have this assumption called the free space, we make the charge density, which is the rho, and also the current density to be zero, and it will make the Maxwell equation to be much easier to analyze. So after making the free space assumption, the Gauss law will look like this, and the Ampere's law will be simply like this. And actually, we need to know this curl of curl identity. Actually, you can check this one on Wikipedia actually, or you can just follow the definition, which we have. We can check the definition of this one. This is the definition of the curl F. This is the definition of curl F. And make use of this, we can calculate the curl of the E field or B field or any vector field. So it look like this, and actually we can. You can take the curl again. So just this one is the new F. This one is the new FC. This one is the new maybe called curl F Z, and then you can take partial Y to this one, so that you have partial Fx, partial Y, and then we have a partial Fy, partial X, partial Y, and then minus this one. This one is actually this term, take the partial C. So we have a partial c to fx, and then we have partial c, partial x, partial z, somehow like that. And actually, you can prove the identity to be like this. Actually, this one is called the Laplacian. Laplacian is actually like gradient, divergence of the gradient of f. So this term is this one. This term is this one, something like this. So as long as you know that gradient is nothing but partial x, I plus partial y, j plus partial z, k, something like this. So we know that this one is nothing but the Laplacian. So we have this term inner product with this multiplied by itself. So it's nothing but partial 2 partial x squared, and then plus partial squared partial y squared plus partial squared partial z squared, something like this. So this is the Laplacian. And just now you know that there will be something like this in this term, but actually we subtract them, and we can, this one is divergence of f, which makes the vector field to be a scalar field, and then we take the gradient again. So it becomes a vector field again. And this is a scalar operator. So actually this one is a scalar operator. This is not a vector operator. So this scalar operator operates on the vector field. It is still a vector field, another vector field. So this one, curl of the vector field is a vector field. So curl of a vector field is still a vector field. So both sides is a vector field. So we have the curl and curl identity, and actually we just need to make sure of it. You don't need to memorize it or whatever. So now we have this one. This one is actually the Faraday's law, and this is the Ampere's law in free space. And this is the Gauss law for the electric field in free space. And we make use of this curl and curl of curl identity. So which means that the left hand side we substitute f vector field by E field. And then the right side, actually we just take the curl to this equation. Take the curl of this equation. Take the curl on both sides. So that for the left hand side we have curl of E. And then for the right side, actually the curl of partial B partial T. The curl of minus partial T partial T. And we assume that the differential sign can be exchanged, because this one take the derivative in the space domain, and then this one take the derivative in time domain. Actually we just assume that can be exchangeable. The order can be exchangeable. So we just put the curl inside. So for the left hand side, we make use of the curl of curl identity. So the left side becomes gradient of this one minus the Laplacian of E. And the right side we make use of the Ampere's law. So the right side substitute to here. And mu naught epsilon naught is actually constants. So we just factor them out. And then here we have partial t, we have another partial t. So this is the second partial derivative to time for the E field. So this one look like this, and here this one make use of the Gauss law, which is actually 0. So this one becomes 0. This one becomes 0. And then both sides have a negative sign, so we multiply, we make it positive. So finally we have this equation. This is one of the wave equation. One of the wave equation for the E field. So it is nothing but the Laplacian of E. So this is the derivative in the space. Second derivative in space. And then this is the second derivative in time domain. And then here is a constant, and actually this is the 1 over c squared. This is the 1 over c squared. So similarly we can derive the wave equation for the B field. So here we make use of the Ampere's law. This is the Faraday's law, and the Gauss law for the magnetic field. So doing the same thing, we take the curl to this one on both sides, to the Ampere's law on both sides. And then also we just substitute, we just exchange the order of the time derivative and the space derivative. So we just plug this one in, and then we use the Faraday's law, so that for the right side we have this minus partial t, and then here we have partial t. So we have a second derivative with a minus sign, and then we also have this term. So the right side becomes this, and for the left side we make use of the curl and curl identity. So we have something like this. Similarly, we make use of the Gauss law for the magnetic field. So this term becomes 0. And similarly, we just multiply -1 on both sides. So this one is the wave equation for the B field. So actually, it just look actually the same with this one. The only thing is we change E to B. So actually we have the wave equation for the E field and B field, and E field and B field. And actually we know that according to the classical theory of the wave, we know that this term is actually 1 over v squared, and v squared is the speed of the wave. And now we know that it is the EM wave, so the speed should be the speed of light. So this v should be 1 over c squared. So should be c squared. And in this case, we know that c should be 1 over square root to mu naught epsilon naught, which is actually the speed of light in free space. If you need to calculate the speed of light in other material, you can just substitute something like mu epsilon for other material. And actually mu and epsilon should be larger than mu naught epsilon naught. So actually this C some sort of material should always be smaller than or equal to the speed of light in free space. So actually, we just make this substitution. The wave equation will look like this, and actually, we can simply solve this equation in one dimension. Actually, just now I mentioned that actually Laplacian in 3 dimension is something like partial x squared plus partial something like this. But we can just make things easier, make life easier. We can assume we only solve it in 1 dimension. Maybe we just rotating the coordination. So we can just solve this in 1 dimension. We assume the EM wave is propagate in x direction. Just assume it's just propagate in x direction. So E and B is just the function of x and t, not y and z. Doesn't relate to y and z. And in this case, we just consider this term for the Laplacian. So next, we try to solve this PDE. So solving PDE is not difficult for some simple PDE. Of course, for complicated PDE, you need some other method like Fourier series expansion or whatever, or you need to use a numerical method. But here, for the simple PDE, we can usually, or at least when you try to solve a PDE, the first method you should try is to use the separable variable. Maybe it doesn't work, but just give it a try. Maybe it works, and it will give you a simple solution. So the separable of variables means, suppose the E field is the function of x and t. So we just assume it to be a function of x itself multiplied by the function of t itself. So they can totally separate, and then multiply together. So in this case, we can just substitute this one into the original equation. So we have the function of x, and the function of time, and then here we also have this one. So actually, for the left side, we take the second derivative with respect to x, and in this case, this function is a constant to the x, so we can just factor it out. For the right side, as long as we take the derivative with respect to time, so which means that Ex is a constant to the time, so we can factor this term out. So this one become Et times the second derivative of x to Ex, and then 1 over c squared times Ex, this one times d2 Et dt squared. Actually, it is just a function of x, so we can use the full derivative rather than partial derivative here. But actually, just some minor issues. So actually, we can just divide Ex Et on both sides. Ex on both sides. So here we just divide Ex Et T on both sides. So in this case, we have this term equals to this term. And note that on the left side is just only the function of x. And on the right side, just pretend you don't see this this one. So on the right side, it is just only the function of time. It is not a function of x. And for this one, it's not a function of t. But actually, they should be the same, which means that this term shouldn't, this overall term is not a function of x. And this term is not a function of time. It should be a constant. Otherwise, they cannot be the same. They cannot be the same. You cannot imagine fx equals g of y, and suppose they are not constant and x is varying, but the other side is not related to x. So you can just imagine if you have a f of x equals g of y, and if f of x is not a constant, which means that fx of 1 equals doesn't equals to fx of 2. But both of them should be equal to g of y. So this is not possible, right? This is not possible, which means that f of x should be a constant, and similarly, g of y should also be a constant. So, which means that they should be equals to a constant. They should be equals to a constant. Now we call it a, or whatever variable you like. So for the left side, we know that this one, the left side should be equal to a, and the right side should be equal to a. And this becomes two second order constant coefficient ODE, which is easy to solve. Actually, we just need to multiply EX to the right side and multiply C squared ET to on both sides. So it becomes these two. So if a is larger than 0, which means that this one is somehow like dx squared minus aex equals to 0, something like this, right? So suppose you need to solve it, you just change the second derivative as s squared minus, and then this is the original, so it's changed by 1, so s squared minus a to be 0, right? So if a is larger than 0, which means that s should be plus or minus square root of a, right? So in this case, it should be two exponential function, and similarly, et should be something like this, which is not what we like to have, because it is exponential decay. Is not like a wave. It's not like a wave. It will something like if x is infinity, this term will go to infinity. This will go to infinity, and for x to be negative infinity, this term will go to infinity, and so it's something like this term is something like sorry, this not this. So so this term will be something like this, and then will exponentially grow to infinity. And for this term, it will be something like this, and depends on what a and b is, and then you subtract, you add them together, and similar for this one. So this is not what we would like to have. It's not what we would like to have. So we just discard this one. And for the next case, if A is 0, which means that we have nothing but partial x e to be 0. So we just integrate it 2 times. So ex would be a plus bx. So you just take second derivative, and then it will be 0. So it satisfies this one. And similar for et, it's similar thing. And this is still what we don't like, because this is a linear function. And this is a linear function. This is not a wave. So for case 2, it's not good either. So for the third case, A is smaller than 0. So in this case, for this one, we have s squared plus A should be, or it should be still minus A. Minus A to be 0. And suppose it is smaller than 0, we make it to be negative k squared. So suppose k is a real number, not equal to 0, then negative k squared should be smaller than 0. So here it becomes s squared plus k squared to be 0. In this case, s should be plus or minus jk. J is the square root of 1, or here I use I, because in the textbook it is used I rather than J. But yes, usually for the physics or mathematical textbook, they like to use I. But in ECE field, usually the textbook will use J rather than I.
I is current.
Yeah. Because we usually reserve I as the current. So for almost all the ECE textbook I've ever seen, they also use they usually use J. So in this case, we know that S is plus or minus jk, which means that the solution should be exponential to ikx and exponential to minus ikx. And here, for the t, it is a little bit different. So it is like s squared minus ac squared equals to 0. So s squared plus k squared c squared equals to 0. So s should be plus or minus j kc. And kc is actually omega. Kc is actually omega, which means that if you still remember, k is 2 pi over lambda, which is the wave number, we have learned. So actually kc will be 2 pi c over lambda, of kc, so something like this. So c over lambda is nothing but f, so it is 2 pi f, which is omega. So here we have exponential to I omega t, exponential to minus I omega t. So it's look like this, which means that omega is kc. So suppose you learn how to solve the ODE, which you should make it the linear combination of this one and this one. So we have exponential to Ex should be somehow like A times this one plus B times this one, and then Et should be C times this one plus D times this one. So you put something like maybe we have E exponential to I kx plus f exponential to minus I kx, and then EFG exponential to I omega t plus h exponential to minus I omega t, something like this. So suppose we have this term multiplied by this term. So we will have this one. We will have this one. Or you can just make C equals to EG. And then for the next one, we may have this term multiplied by this term. So we have IKX multiplied by negative I omega t. So IKX minus, so we have this one. So we have this one. And then next one, we can have this term multiplied by this term. So we have minus IKX plus minus IKX plus I omega t. So we have this one. So we have this one. So we have this one. Minus IKX plus I omega t. Yes, right. So finally, we have this term multiplied by this term. So minus IKX minus I omega t. So it should be this one. It should be this one. So we have all things like this. And actually, we can just group them together. And here, we can see that we have kx minus omega t. Kx minus omega t. And it means that it propagates in positive x direction. And for this one, we have kx plus omega t, kx plus omega t. No matter it is a plus or minus sign, it is propagate in the negative x direction. So, which means that for these two terms, it is actually in x direction. In x direction, this wave is propagate in this direction. In this direction, and for this term, it is propagate in that direction. In that direction, and actually A and B only related to the phase and amplitude. To the phase and amplitude of the two wave. So actually you learn something similar in signal and system. So I suppose you should get some idea about this crazy stuff. So actually we will say that a wave is propagate in positive x direction, a wave is propagated in negative x direction. So for simplicity, we can just consider one of it is enough. So in this case, maybe we can just ignore this one. So we only care about the wave propagate in positive x direction. And actually, this is a complex function. But actually, the EM wave exists in the real world, so it should be a real function. You can see it's a real differential equation. It's a real differential equation. which means that this one should be a real function also, and it should satisfy A should be B conjugate, and in that case, when they add together, they will become a real one, and the negative and the imaginary part will be cancelled with each other. Because if B is the conjugate of A, which means that it will something like exponential to I something, and then plus A conjugate exponential to minus I something. So this whole thing is the complex conjugate of this one. Is the complex conjugate to this one. So which is something like, this is A plus JB, or this is A minus JB. So the imaginary part should be cancelled. So it turns out to be 2A, something like this. So it's just a real function. So actually, we know that this is exponential. I something, which means that the real part is cosine. The imaginary part should be sine. So it turns out it is a cosine this stuff, cosine kx minus omega t, and then this is the E, so it is just EM, which is the amplitude of the E field. So making use of the Faraday's law, and then we substitute this solution to this one, and then we consider the one-dimensional case. So it is nothing but partial E partial x equals to minus partial B partial t. So we just take the partial derivative of x with partial derivative of E with respect to x. So this is kx. So k comes out by the chain rule, and then this is cosine. So this become minus sign. So we have another negative sign. So it becomes positive KEM sine of kx minus omega t. And then we can just integrate both sides. So this is partial t. So we make it here. So it becomes dt, and then integration, So the left side becomes bx of x and t. And then the right side, we take the integration. Here we have a minus sign, and then we integrate the sign. So we have two minus signs, so it becomes positive. And then we integrate with respect to t. So we need to divide omega. So we have k omega times EM cosine kx omega t. So actually in the textbook it tells you that this one and this one should be the same. And actually k omega EM is nothing but BM. So EM over BM is omega over K. And just now we already show that omega is KC. So omega over K. Omega is KC. So K and K. So it's equals to KC over K. So it's nothing but C. So the ratio, the amplitude ratio of the E field and B field should be the speed of light. And then finally, suppose it exists in a three-dimensional, and actually this is called a plane wave. because it only related to the E direction, It does not relate to the Y and Z. Does not relate to Y, Z. So suppose given an X, and then you vary over the Y and Z space. Actually, the E field should be the same, which means that it's just like a plane. And actually, we can generalize it in the three-dimensional. So K can be a vector in three-dimensional, and X become R vector, and then they take the inner product. So this becomes the three-dimensional plane wave. This becomes the three-dimensional plane wave, and R hat is the propagational direction. Actually, K also have the same direction, because as long as they have the same direction, they have inner product. Otherwise, it becomes solid. So maybe I can open it in. Maybe I show you later. Okay. So for the energy density, we also know that EM is the amplitude. EM is the amplitude of the E field. BM is the amplitude of the B field. So the root mean square should divide both term by square root of 2. And previously we have learned that the energy density should be 1/2 epsilon naught E square, and for the magnetic field it should be 1/2 mu naught B square. Because previously I already tell you that for the same topology, then you usually exchange E by B and then exchange the epsilon naught to be 1/mu naught. So they should be something similar. And in this case, UE is this one, and we know that E should be C times B, because we know that E over EM over BM should be C. So we have E equals CB. So suppose we expand it. It distributes the square to C square B square, and C square is nothing but 1/mu naught epsilon naught. So this one is 1/mu naught epsilon naught, and epsilon naught can be cancelled. So finally it becomes B square over 2/mu naught, which is nothing but UB, which means that the energy stored in the E field and the B field within the EM wave should be the same. The energy stored in the E field and the B field for the EM wave should be the same. So in this case, the total energy per volume, in the EM wave should be you add UE and UB together. So as long as they are the same, so it's just like 2 times 2 UE, which is epsilon naught E squared. So the Poynting vector is actually the energy per time per area. Per time per area. So the magnitude of it should be the energy time per area. This is divided by the volume. Divided by the volume. So you should multiply by the length, by the propagation length, and then divide by the time, which is nothing but the speed, nothing but the velocity, which is the c. So you can see that c is actually c is so now we have e squared, which is so you can change it to EBC. So E squared should be EBC, and then we have epsilon naught C squared, still C. And then totally we have C squared, so it becomes mu naught epsilon naught, and then we have epsilon naught EB. So we can subtract, you can cancel epsilon naught. So that's why the Poynting vector is E vector cross B vector over mu naught, which you'll have see it on the textbook. So it's something like this. So let's have a 15 minutes break.